Information obtained from physical experiments is often used to decide how to design, develop, or manufacture a product. How often do you rely on experiments and the resulting data to make your decisions? If you're an engineer, the answer is probably quite often. If you're a manager and not directly involved with formal experimentation, you probably still use the data derived from the experiments to make decisions. We can't talk about data or decision-making without the word statistics entering the conversation. Although the term statistics is familiar, not many of us are familiar with how statistics can be used. Statistics is not just tables and graphs of numbers that can be manipulated to support or deny an argument. Statistics, as it is applied to the planning and collection of data, can impact timeliness, validity, quality, and comprehensiveness of scientific data. Data, in turn, can be used to improve the design of a product as well as the quality of the manufactured hardware. You may question the role of statistics in an engineering environment and how it can affect scientific data. We hope to demonstrate exactly how and why statistics is a valuable tool as it affects scientific data in physical experiments. But in fact, statistics is more than just a tool. It is a way of viewing the world around us. It constitutes a way of quantifying and interpreting the realities of variability in physical phenomena, whether they be production processes, product design and product function, marketing trends, or accounting practices. The statistical point of view touches almost every aspect of our work, but we often ignore its presence. In engineering, we tend to think in very precise terms, and we pride ourselves on a first principles approach to problem solving. And yet, everyone knows that a theoretical approach to modeling actual events requires verification of their appropriateness. Verification for appropriateness requires observation of the process at work. Observation of the process at work means the collection of data in an environment subject to variable conditions. But the presence of variable conditions means the need to design and interpret experiments statistically. Today, American industry is hearing a lot about productivity and the quality of manufactured goods in Japan, and rightfully so, for the Japanese have been most successful. The reasons for the success of the Japanese are many, and it would be an oversimplification to point to one single factor. But there are some observations. Since World War II, when the Japanese began to reconstruct their industrial sector, statistical methods have been central to their efforts from practically day one. In Japan, statistical methods for quality control are widespread, touching almost all major industries. Most Japanese companies provide statistical training for employees as part of the normal conduct of activities and operations. More than 65% of all engineering personnel in major industries have received some formal statistical training. And in Japan, statistically designed experimentations have been most valuable in product design. These are the facts, and at a minimum tell us one thing. The Japanese make widespread and extensive use of statistical methods in product design and production processing. Too often we think of statistics as something we do to data after we have it in hand. The role of statistics in the design of experiments and the collection of data is not as well recognized. The objective of this presentation is a simple one: to acquaint you with the role of statistics in the planning and conducting of experiments, and to demonstrate some important fundamental practices for sound design of experiments. By example, we will discuss some inherent problems with experimental work and how statistics can be employed to deal with those problems. The following scenario depicts the adventures of a new engineer named Mike, a more seasoned co-worker named Dick, and their manager Sam. Sam has encountered a problem with part shrinkage for an injection molded component. The shrinkage is too large and is causing a problem in assembly. In this example, the shrinkage values are coded by multiplying the percentage of shrinkage by 10. We begin in Sam's office.
Okay, we've been given the assignment of studying the injection molding process. It seems that when certain parts are molded, they experience excessive shrinkage. I'm giving the project to the two of you. I'd like you to study the injection molding process, then determine how shrinkage can be reduced.
Sam, I think we're in luck. I worked in plastics before and have a lot of experience with injection molding machines. I can guarantee you I know just what the problem is right now. The mold temperature is too high. We all know that mold temperature is the single most important factor that affects part shrinkage.
Well, Dick, we also know that injection molding is a fairly complex process. There may be more than one factor that influences shrinkage. I think you should run some tests using the injection molding machine in the lab.
Don't worry. We'll have this problem solved in no time at all. I'll solve this problem by the end of the day and impress Sam with my ability to quickly get to the heart of the problem. With Mike's help, I should be done with the testing by noon. Kid is young and inexperienced, but I'll do him a favor. Show him just how we approach such a troubleshooting task in industry and get the job done. Here's the plan, Mike. We'll run two tests, one at a low temperature and one at a high temperature. This will prove to Sam that reducing temperature will reduce shrinkage. I told Sam this was the answer. Just look at those results. High temperature is 21.5% shrinkage. Low temperature is 17.1% shrinkage. Let's get this to Sam right away.
Whoa, wait a minute, Dick. Don't you think we ought to run another test?
Why bother? There's the results. Let's call Sam on the phone and tell him the good news before lunch.
Well, I took a course in statistical experimental design last semester in college, and they really stressed the importance of replicating experiments in order to observe and measure experimental error. Running the same test 2 or 3 times will produce different results. You have to judge the average difference you observe against the possibility that it could have occurred solely by chance.
It doesn't make sense to waste time. We've already got good results. Just to make you happy, I'll run another set of tests. It's almost 10:30. Turn up the screw speed so we can get these 2 repeat tests done faster.
Dick, if we increase the screw speed, we may run into a problem.
Hey, kid, did I tell you I was going to buy you lunch today?
I can't hear you. Increasing the screw motors makes you switch going.
Hey, you didn't mix up these specimens, did you?
No, I was very careful in making the shrinkage measurements. Why?
Well, look at these results. At low temperature, the shrinkage is 27.6%. And at high temperature, the shrinkage is 15.4%. The shrinkage is much worse at the low temperature, but even better at the high temperature. You must have reversed the results on the data sheet. Hand me that eraser.
No, wait. I knew we shouldn't have messed with that screw speed. Now, that probably affects shrinkage, too.
No, screw speed has nothing to do with shrinkage. I know. Remember, I've worked with injection molding before. But I did notice that the holding pressure has dropped some since the first tests. We better readjust holding pressure back up to the original level and run one more test at the higher temperature. Look at this test result. I can't believe it. Now the shrinkage is 28.2%.
I'm afraid we're playing around too much with these machine settings. Things are getting all confused.
No, I think I know what the problem is. In the past, I've sometimes had to increase the gate size when I've had shrinkage problems. Hey, give me that hand grinder. I'll open up the gate a little. See? Shrinkage has been reduced a little. Now it's 23.8%.
That's still not good. We had early test results around 15 to 17%.
You know, that high temperature test we ran after we increased the screw speed was done when the holding pressure had drifted lower. Maybe we better reduce the pressure and run just one more test.
Well, you know, it's 11:45. I'm getting hungry.
Well, hold on for a little while. We've almost got this solved.
Well, maybe we should reduce the screw speed, too, so we're back to where we started.
But remember, for those first 2 tests, the lower temperature gave better shrinkage results, just like I knew they would.
You're right. Let's reduce the temperature, too.
Now, you must have read the shrinkage incorrectly. Now we have 22.1%. That's still too high considering all that we learned this morning.
Look, my reading is correct. We never should have opened up the gate.
Well, I'll fix that. Push that arc welder over here.
This is ridiculous. We still have shrinkage of 20.3%. We can't even get close to what we had in the first few tests.
I'm getting confused. I can't remember what we've done. All right, let's try something different. If I recall correctly, a few months ago, we had an injection molding problem, and we solved it by lengthening the cycle time.
Now, maybe we ought to break for lunch. Talk this whole thing over. I mean, I don't think we're coming at this problem correctly.
Listen, kid. I've been fighting brush fires here for years. But you're right. I'm getting hungry, too. Let's break for lunch. No, we've tried everything. Still, the results are bad. We changed the mold temperature, screw speed, gate size, and holding pressure, and still can't find the correct combination.
Well, maybe our whole approach is wrong. Maybe we shouldn't be looking for these single correct machine settings. Maybe we need to be more scientific about this. Now, we've changed lots of things. The results vary all over the place. I think we should be carefully studying the influence of all of these factors on shrinkage in an organized fashion.
You kids just don't realize what it's all about here. We haven't got all day to solve problems with those fancy, time-consuming experimental design techniques you learn in college. Those professors out there were never under the gun. They don't know what it's like out here in the real world.
But we've run tests all morning. We're no better off than when we started. We haven't learned anything.
Okay. We'll try it your way. Let's go back this afternoon and methodically study each factor, one by one, with all other factors fixed. Then we'll see the clear effect of each factor on shrinkage. Then we can plot a whole series of curves, one for each factor, and pick off the optimum values for shrinkage for each factor.
Well, I don't think that's such a good idea. You remember when we ran the first two tests to study the effect of the mold temperature, and we repeated the test with the increased screw speed? The results of the repeat test were opposite from the first two tests. Now, that tells me something very important.
Yeah, it tells me not to mess with the screw speed. That's why we should look at things one at a time.
No, it says a lot more than that. Maybe the effect of mold temperature on shrinkage depends on the screw speed. The mold temperature-shrinkage relationship could be very different depending on the level of the screw speed.
Oh, so what? We just won't change screw speed when we study the mold temperature. We'll hold speed absolutely constant.
Okay, but what screw speed will you pick?
Well, any speed, it doesn't matter. Oh, I think I see your point. All right. How do you think we should handle this problem?
We'd better study the process variables in order to reveal the interaction which may exist among them in a joint test plan. Let's go back to the office. I'll show you how we can do this with only a few tests.
While Dick and Mike are trying to design a plan for experimentation, let's look at some of the common pitfalls in experimental work that Dick fell prey to. First of all, Dick entered into his experimental tests with a strong preconceived notion about what was wrong and what would solve the problem. He therefore designed a very narrow experiment to support his conviction. Since his original notion was incorrect, the results from the test left him with no basis to move forward with more experiments in an informed fashion. He simply continued to guess what might solve the problem. We can see that although past experience is a tremendous guide in conducting physical experiments, it sometimes promotes tunnel vision and may lead one down the wrong path. This may happen in any experiment. But the key here is to be able to recover quickly and move in the right direction. Dick also failed to recognize the importance of getting input from a variety of sources. No one person should have responsibility to completely design and conduct an experimental program alone, particularly if they are very close to the problem or an expert in the area under study. Scientists and engineers should design and run their own experiments, but they should be aided by others who can ask the right questions and provide statistically oriented guidance. Dick failed to identify the presence of variability in data and how repeating tests can be used to determine the level of uncertainty in the data so that results can be interpreted in light of the variability in the experiment. Let's get back and see what Mike has to offer toward the solution to this problem.
Now, first, we should list all the variables or factors which could potentially influence shrinkage. Then we should use all past experience. But let's be careful not to be too close-minded about what will or will not have an effect. All factors are probably not important, but the question is, which are the important ones? Now, we're looking at the problem of screening variables by using a designed experiment.
All right, let me make up a list. Here's a list of 7 factors that may be important. The mold temperature, moisture content, holding pressure, screw speed, booster pressure, cycle time, and the gate size.
All right. Well, we really should do some type of factorial experiment. This will allow us to vary factors together.
Yeah. And in order to get a good idea about the way changing a factor affects shrinkage, we better have at least 4 levels of each factor and look at all possible combinations.
But, well, if we do all possible combinations of 7 factors over 4 levels each, that's, well, let's see. Well, too many tests. 4 to the 7th power is 16,384 tests.
I see. It's not so easy, is it? Let's get rid of some of the factors. If we study only 4 factors, that's only 256 tests.
All right, let's see. It takes 30 minutes per test with breaks for food and sleep. We'll have to work for weeks. Besides, I think it's better to look at all 7 factors and reduce the number of levels. In the beginning of an experimental study, it's better to look at many factors over fewer levels rather than few factors over many levels. So I think we should look at each of the 7 factors with only 2 levels of each, a high and a low level. Initially, our objective should be to quickly screen out the unimportant variables.
No, we'll still have too many tests. 2 levels at the power of 7 is 128 tests. Still doesn't solve our problem.
Well, Dick, in that experimental design class that I took, I learned that if we have 4 to 5 or more variables, we generally don't need to run all possible combinations. Only a fraction of them are really required. In this case, I think we could start out with only 16 tests.
16? How will that give us valid results?
Hear me out. 2-level fractional factorial designs are a very powerful experimental design tool. The key is to pick the right 16 tests. If we were to run 128 tests, we would obtain a lot of information, but most of it wouldn't be relevant at all. For example, if we ran 128 tests, besides the average main effects of each of the 7 factors and the 21 2-factor interactions, we'd also get estimates of many other interactions which are probably not that important, such as 35 3-factor interactions, 35 4-factor interactions, 21 5-factor interactions, 7 6-factor interactions, and 1 7-factor interaction.
Yeah, I think I see your point. Do we need to know about interactions above 2 factors?
Well, that is the point. These interactions are likely to be negligible, and initially we should be satisfied with the information on the average main effects of the 7 factors and some idea about potential 2-factor interactions. Then once we narrow the list of variables, then we can run more tests in detail. The purpose of the initial stages of experimentation is to identify which variables have a sizable influence on the shrinkage. And eventually, through further experiments, we will be able to determine more precisely how individual and simultaneous adjustments will influence the shrinkage.
I don't like the sound of initial stages of experimentation. We can't make a big production out of this. Let's design one big experiment, and that's that.
Oh, wait a minute. It's important to experiment sequentially. It's important to build up knowledge which will guide us as we move along. If erroneous decisions are made planning one big experiment, the results may be disappointing. With one big experiment, all of our resources could be expended. All right, so how many tests do you think we can reasonably do in the entire study in terms of time?
Probably 50 or 60 at the most.
Then 16 tests in the beginning should be just about right. In the first experiment, we should never run more than about 25% of the total tests we plan to do overall.
Okay, I think we're on a roll. Specifically, which 16 tests should we do?
I'll set up a test matrix. I'll be back in a little while. All right, Dick. Here's the matrix. Now, the plus and minus signs are the high and low levels for each factor. Factors are listed across the top of the page. Mold temperature, moisture content, holding pressure, screw speed, booster pressure, cycle time, and gate size. Now, each row of plus and minus signs defines the settings for a test.
Great. I'll get to this right away. Mike, don't you have anything to do? I can do this alone, huh?
Okay, I'll get back to that laser project I was working on. Oh, by the way, Dick, make sure you randomize all the tests. Well, don't run them in the order on that data sheet, or else you may have some problems.
Okay, just leave it to me. Huh?
Okay.
Randomize? What for? Oh, it's going to take me years to get those fancy statistics notions out of his head. Let's see. I can run about 1 test per hour, so I can finish in 2 days. I have 2 bags of plastic pellets, and I can get about 8 tests per bag, so I'm in good shape. Well, here are the test results. Some of the test combinations you suggested produced very low shrinkage values, 15% or less. The best result is 14%. Let's go tell Sam so he can issue an order to run production at these conditions.
Oh, wait a minute now. Remember, we said we wanted to fully analyze the data to determine the size and the direction of all the variable effects so that we could try to determine exactly what adjustments lead to the improvement. But before we do the analysis, why don't you tell me a little bit about how you actually conducted the tests? Like, how many tests did you perform each day? What order did you test in? And what raw material did you use?
Well, I did things in a very orderly, systematic, scientific fashion. I did 8 tests a day, 4 in the morning, 4 in the afternoon. I found 2 bags of raw material in the stockroom, so I used 1 for each day's tests. I left the machine on over the lunch hour to avoid the need for a warm-up period in the afternoon. As far as the order in which I ran them, you had the test numbered 1 to 16. I ran them in that order.
But I thought I mentioned that you should randomize the test order.
Randomize? What does that have to do with it?
Well, quite a bit. I'm afraid I got some bad news for you. All of these tests may be invalid.
Don't try to be funny at a time like this. I'm in a hurry to get these results to Sam. Let's get on with the analysis or whatever the next step is.
Dick, I'm not trying to be funny. You've made a very basic error in conducting the experiments, and it can't be solved through analysis. It's the experimental procedure that may be invalid.
Well, I know you're busy these days with other projects. I'll have Jack help me with the analysis.
No, that's no good. Your results are likely to be totally misleading. Just let me explain. First of all, those 2 bags of material may have come from 2 different suppliers or 2 different batches. Now, even though the chemistry is supposed to be the same, it's probably not, due to supplier or batch-to-batch differences in actual material and preparation. If you look at the table of tests I gave you, you'll see that the 8 tests with the low screw speed were done first, and then they were followed by the 8 tests at the high screw speed. That means the screw speed levels exactly coincide with the 2 bags of material. Any effect that raw material may have on shrinkage is confused with the screw speed effect. And furthermore, the different raw material sources may inflate the level of experimental error and make it more difficult to clearly see the real variable effects. Also, look at the plus and the minus sign columns associated with the holding pressure. All of the plus levels were afternoon tests, all of the minus were morning tests. Now, due to the warm-up effect, the machine may perform better after it's been on for a few hours. Now the warm-up effect is confused with the holding pressure effect.
Well, can't we work this out in the analysis?
Afraid not. It's too late. The problem is one of actual test conduct. You're going to have to rerun these tests.
Yeah, I noticed the machine was vibrating some. I'll tell Sam there was a problem with the machine and I have to do the tests again.
Tell him what you want. But this time, let's do it right. Often unknown factors varying out of control during the experiment can produce trends in the data, such as the machine warm-up effect. And we can counteract these forces by randomization to avoid biasing the data in a particular direction. This way, we guarantee approximate validity of the test procedure. This is why I suggested that you randomize the test in the first place. And further, when known sources of nuisance variation are present, such as the fact that the raw material came from different suppliers or batches, we can block out this variation. Without blocking, the experimental error is inflated by large differences in performance which may occur solely due to the difference in materials. These large differences in performance, due to the material, could mask the presence of the real differences in performance of the variables we are studying in the experiment. In this experiment, we can run the 16 tests in 2 blocks of 8 tests each, 1 for each material bag. This actually amounts to adding an 8th variable, the raw material, with 1 of the bags for minus tests and 1 of the bags for plus tests. In this way, we will separate the material effect from the other variables. We'll even be able to see if the shrinkage is different for different material batches. All right, Dick. Here's a randomized test sequence for you to run. Now run them according to the test order that I've established. In this case, it would be inconvenient to totally randomize because of the changing raw material from test to test. So we'll randomize within each block, but run all the tests in block 1 first, then block 2.
You've been very helpful. I think this series of tests will give us valid results. I'll start on the test immediately so I can give Sam the answer he needs.
While Dick's performing the tests in the correct manner, let's go back and review what he has learned from this experience. Dick, first of all, failed to appreciate the notion of variability that is inherent in the experimental environment. The same test conditions replicated produce different results. This will naturally occur due to many factors which by themselves are of little consequence, but when aggregated tend to produce an observable variability in data. To determine the magnitude of experimental error, some replicate tests should be performed. Dick initially failed to appreciate that factors are often related in terms of the way they influence experiments. Variable interactions or interdependencies, more often than not, are the key to solving a problem. Mike met this problem head-on by designing the experiment using the two-level fractional factorial. This way, he could obtain estimates of the interactions from the data. Dick did not appreciate the sequential nature of experimentation, the notion that the experimental procedure should enable one to move from a state of little knowledge to a state of advanced knowledge by a process of elimination of unfruitful paths and an elevation of fruitful paths for future study. We should think of experimentation as a four-stage iterative procedure. These stages are conjecture, design, experiment, and analysis. The design should be made to test the initial conjecture, and the analysis of the data should lead to a new conjecture, followed by a new design, and so on. Dick also failed to recognize that certain unknown forces could be influencing results over a series of experiments in a structured or correlated manner that produce a trend in the data. If the tests are run in a similarly structured manner, such as all tests with low holding pressure in the morning and all high holding pressure tests in the afternoon, then the trend due to the unknown force could bias the results. To counteract such forces, randomization is required. Dick also failed to recognize that known sources of nuisance variation could introduce unwanted variation in the data and inflate the experimental error. Even if randomization does distribute the nuisance variation so it affects all things equally, another concept called blocking can eliminate altogether some sources of error. Now that Dick has learned some important lessons in how statistics can help with the planning and conducting of an experiment, let's see what the data actually reveals.
Mike, I've completed all the tests in the manner we've outlined, and I'm ready to analyze the data. Here's a table of the results. Shrinkage values range from 14 to 27%.
Good. I'll take the data, do some calculations, get back to you later.
Thanks. That'll give me some time to make some phone calls.
It is now 4 hours later. Additional experimentation has been completed in order to isolate the significant two-factor interaction.
Dick, have the results. Look pretty interesting.
Well, what took you so long? Sam's been bugging me about giving him the results.
Well, relax, and I'll explain what I did. Now, the complete analysis of this experiment is somewhat involved, but let me explain some of the key elements of this type of experimental design by examining only a portion of the results. Now, let's focus on two of the variables, screw speed and holding pressure. Now, this can be thought of as 2 to the power of 2 factorial, which geometrically can be represented as a square. Now, the 4 tests required are the corners of the square. Now, in this geometric representation, there are 2 comparisons that we can make which say something about the effect of holding pressure when screw speed is held constant. At a low level of screw speed, increasing holding pressure increases shrinkage by 0.9%. At a high level of screw speed, increasing holding pressure increases shrinkage by 10.1%. Then on the average, Increasing holding pressure increases shrinkage by 5.5%. We call this the average main effect on holding pressure. We can do a similar calculation with the screw speed. In this case, the average main effect of screw speed is, it's like 1.2%.
Hey, this is simple. Let me see if I understand. On the average, increasing holding pressure increases shrinkage, and increasing screw speed increases shrinkage. Then to reduce shrinkage, we should reduce both holding pressure and screw speed.
We have to be careful here. Look at the results more closely. If we examine the screw speed effect more carefully, we see that it is different depending on the holding pressure. When holding pressure is low, increasing screw speed actually decreases shrinkage. But when holding pressure is high, increasing screw speed increases shrinkage. The average main effect of screw speed alone is somewhat deceiving. These two variables interact in terms of how they influence shrinkage. Now, we can determine the degree of interaction by looking at the average difference in the individual main effects. At low holding pressure, the increasing screw speed decreases shrinkage by 3.4%, whereas at high holding pressure, increasing screw speed increases shrinkage by 5.8%. Now, the average difference in these two effects is therefore large, 4.6%, which means that a strong two-factor interaction is present. And we can represent the average main effect and interaction effect information we've obtained from the experiment as an equation to predict shrinkage as a function of holding pressure and screw speed. Shrinkage at any given values for holding pressure and screw speed is equal to the average of the four tests forming the square plus the average main effect of holding pressure over 2 times the holding pressure plus the average main effect of screw speed over 2 times the screw speed plus the interaction effect between holding pressure and screw speed over 2 times the product of holding pressure and screw speed. Numerically, this equation is percent shrinkage equals 19.75 plus 5.5 over 2 times holding pressure plus 1.2 over 2 times screw speed plus 4.6 over 2 times holding pressure times screw speed. Now, we notice two things about this equation. One, the interaction effect coefficient is quite large. It is a significant part of the equation. And two, in terms of the square, shrinkage is predicted to be smallest when holding pressure is at its minus level and screw speed is at its plus level. Because of the presence of this strong interaction, shrinkage is not lowest when both holding pressure and screw speed are at low levels. Actually, the combination of high screw speed and low holding pressure will tend to reduce shrinkage the most. It's the interaction between the screw speed and holding pressure that's the key here.
But it seems we ran this test at the very beginning. Why didn't we see it then?
Well, we did run this test, but because we were testing in such a haphazard fashion and not running experiments, we didn't realize what we had. When you increased screw speed to rerun the mold temperature tests, we got two different shrinkage percentages. Now, you were so preoccupied with finding a nice temperature effect that you shrugged off the downward drift in holding temperatures during the test. You thought it messed up the test, so you quickly increased the holding pressure. When you did that, shrinkage increased greatly. The screw speed you thought was unimportant turned out to be quite important. Further, it was the interaction between holding pressure and screw speed that is the key here to solving the problem. Now, the one factor at a time experiment you wanted to run would never have revealed this.
You really know how to turn the screw.
Well, I just hope you learned something from the experience.
Hey, I really have. Hey, Sam will be so pleased with my performance on this project. Yeah, I know you're busy. I'll save you the time and show Sam the results myself.
Wait, I'm coming with you.
Oh, really?
I'm very pleased with the teamwork you two have displayed. Dick, with your experience in plastics, and Mike, with your background in statistics, you've been able to come up with a solution to the problem. Thanks. I'll pass the information on to everyone concerned.
Dick may not have learned humility from this experience, but hopefully he did learn some important concepts he can carry with him when he plans and conducts experiments in the future, such as the importance of not prejudicing experimentation with preconceived notions of the results, the nature of variability and the importance of test replication, the importance of recognizing the potential presence of variable interactions and how they may be determined through planned experimentation. The fundamental difference between testing haphazardly to hit upon an attractive result and experimentation, which reveals the magnitude and direction of variable effect. The power of using only a fraction of a full factorial design to study many variables in relatively few tests. The importance of randomization to counteract unknown sources of nuisance variabilities. Blocking as a tool to eliminate known nuisance variation. And if the experiment has been properly designed, the analysis of the data is straightforward and easy to perform. The scenario we have just seen with Sam, Dick, and Mike typifies a very common application of statistical experimental design techniques in the manufacturing process troubleshooting. When process performance deteriorates or when erratic behavior is present, these techniques may be a powerful means to comprehensively evaluate the relationship between controllable factors of the process and measures of the process performance. But keep in mind that the methods of planned experimentation have far broader applications beyond manufacturing process improvement. Some candidate areas for the use of experimental design areas may include new process development activities, which make use of pilot plant studies, prototype development, and process simulation employing computer-based models. By using this method, alternative approaches can be comprehensively studied in order to enhance all phases of decision-making. For example, one area where the methods of planned experimentation is most useful is in the area of engineering design, where new products are developed and existing ones improved. Planned experimentation may be used in the evaluation of basic design configuration as well as the evaluation of raw material alternatives. It may also be used to study the effects of external factors on product performance in determining component tolerances and comparing life testing of new product designs. The impact of using these methods in new product design will not only lead to better product performance, but also will significantly reduce product development lead time as the market demands. As we have seen, the Japanese have made extensive use of planned experimentation in product design. They have found out that longer product life and more trouble-free field performance were a result of using this method. This leads to the reduction of design lead time, the reduction of material cost, and the reduction of overall costs in general. Planned experimentation is known in Japan as offline quality control, but it is basically the same thing that we have been talking about in this program. Both methods address the product cycle at the earliest point and attempt to design quality and life performance into the product through experimental considerations. These considerations include component and system design configuration, component material selection, component and system tolerance determination, and the influence of external factors on process performance. Whether we are concerned with engineering design, research and development process design, or process troubleshooting, the proven methods of planned experimentation have an important and real application to all areas we are dealing with. Remember, this method is more than just a useful tool which may be applied in some cases. It should be considered as an integral part in the conduct of the activities we have outlined. This concludes our presentation on planned experimentation.